Hey guys, Mr. McKinney here, just going through another example involving applications of differential equations. This example is going to involve tangent line equations and looking at whether they will give you an over or an under estimate when dealing with differential equations. So again, differential equations are just equations that have a derivative in them, and the derivative just means the slope or the rate of change. Now, if you're ever asked to write the equation of a line or the equation of a tangent line, you should always be using point slope form. So y minus y1 equals m times x minus x1. On this type of problem, they will likely give you the point. So they'll give you x1 and y1. You'll have to figure it out sometimes, but usually they'll give it to you. And then the slope is going to come from the differential equation. So whatever dy dx is equal to, that is your slope. Those mean the same thing. So if we get an equation for dy dx, we can find the slope from that equation by just plugging in the values. Now, once we have come up with an equation for the tangent line, if we're using that to estimate the function, we need to look at the concavity, which will come from the second derivative, to figure out if it's an over or under estimate. So let's look at a concave up graph and a concave down graph. Now on this concave up graph, it doesn't matter whether I'm on this part or on this part or at the bottom. This tangent line is always below the actual function. So if the original function is concave up, then our tangent line is going to be an underestimate because we are below the function. And remember, you can find out if it's concave up if the second derivative is positive. And if the second derivative is negative, it's going to be concave down. And it doesn't matter where you draw the tangent line on a concave down function, the tangent line will always end up being above the original function. So it's always going to be an overestimate. So if you're asked to figure out if your tangent line approximation is an over or an underestimate, you need to think about the concavity, which will come from the second derivative. Now, if we start with a differential equation, we're already starting with the first derivative. So we're just going to need to think about one more derivative of that, the second derivative. So let's look at a recent AP exam question. So again, don't copy all of this down. I'm going to read through this and then we're going to simplify it on the next slide. So at time t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees Celsius at time t equals 0. And the internal temperature of the potato is greater than 27 degrees for all times t is greater than 0. The internal temperature of the potato at time t minutes can be modeled by the function h, which satisfies the differential equation dh dt equals negative 1/4 h minus 27, where h of t is measured in degrees Celsius and h of 0 is 91. So this is telling me that my initial temperature, internal temperature is h, so my initial temperature is 91 degrees. When t equals 0, the initial temperature is 91, which is what it told me already. We're going to do two things with this one, and we're going to do it on two separate slides. We're going to write an equation for the tangent line at t equals 0, and then use this equation to approximate the temperature at t equals 3. And then based on the second derivative, we're going to determine whether our answer in part A is an underestimate or an overestimate of the actual temperature. Remember, we're just going to be looking at whether it's concave up or concave down to determine if it's an over or underestimate. All right, so this is what you're going to want to get copied down into your notes. Given that dh dt is equal to negative 1/4 times h minus 27, and we have an initial condition, we want to first write the equation for the tangent line to the graph of h at t equals 0. And then we're going to use this equation to approximate the internal temperature of the potato at time t equals 3. So again, anytime we do an equation of a line, whether it's a tangent line or any other line, we're always going to use point slope form when we're in calculus. Now in this case, we're not using x's and y's, we're using h's and t's. So we can think about this as h minus an h value, in this case 91, equals, and then m is what we're going to find in a second. Instead of x, we're going to use t, and our x1, this is my t1, this is my h1, sorry, not y1, h1. If we think about it in terms of t1 and h1. So t minus 0. So we just need to find the slope. They already gave us the point in the original problem. We just need to find the slope. And the slope comes from the differential equation. So negative 1/4 times h minus 27. dh dt means slope. This is the slope. So I just need to plug in my h value, and my h value at t equals 0 is 91. So I just need to do negative 1/4, 91 minus 27, which would be negative 1/4 times 64, which would be negative 16. So that is my slope. My slope is negative 16. This is fine for my tangent line equation. You can solve for h, so distribute that. Negative 16t, don't need to worry about the 0, plus 91. It would be okay if you wrote it as y equals negative 16t plus 91. I think it would be fine if you wrote it as negative 16x plus 91. They're looking to see that you knew that the differential equation meant slope and that you used either point slope form or one of the other ones. I highly recommend point slope form. Now, once we've got our equation, we've done the first part. We wrote the equation of the tangent line. We need to use this equation to approximate the temperature. So let's do that in green here. So I need to know at t equals 3. So I'm going to use this one. So we're going to say h equals negative 16 times 3 plus 91. So negative 48 plus 91. And that will give me 43 degrees. The units aren't in this part of it, but it was 43 degrees Celsius. So when t equals 3, the temperature was 43 degrees Celsius. Now keep in mind that this asked you to do two different things. All right, now let's look at part B, which asked us to use the second derivative to determine whether my answer from part A is an underestimate or an overestimate of the internal temperature at time t equals 3. So if I start with dh dt, and I want to find d squared h over dt squared, I want to find the second derivative, I'm just going to take the derivative. Now, I think for me it's easier to think about this problem if I distribute the negative 1/4 first. So negative 1/4 h plus 27/4. This way, when I take the derivative, I don't have to worry about product rule or anything like that. So the second derivative of h with respect to t is going to be the derivative of these two things. So negative 1/4, and the derivative of h with respect to t is dh dt. The derivative of a constant goes away. So I have negative 1/4 dh dt. So I need to plug my equation for dh dt back in. So I've got negative 1/4. School's out, woo! Times negative 1/4 times h minus 27. So this one, the negative 1/4 h minus 27, was my dh dt. And then I have another negative 1/4 out front. And again, this is what the second derivative of h is equal to. So I can multiply negative 1/4 times negative 1/4, which is positive 1/16 times h minus 27. Now, we don't know what h is at t equals 3. But in the original problem, it told me that the temperature was always greater than 27. So if this temperature is greater than 27, this will be a positive number, and this will be a positive number. So this is going to be greater than 0. I don't know what it is, and I don't need to know what it is. I just need to know whether it's positive or negative. In this case, it's positive. So if the second derivative is positive, that means the original function is concave up. So that would mean that h is concave up at this point, at t equals 3. So we're almost done. We just need to answer the actual question. So my answer from part A is either going to be an under or an overestimate. If I'm concave up, the tangent line will always be below the graph. Therefore, it's going to be an underestimate. So we would say that our answer from part A is an underestimate because the second derivative is greater than 0 at t equals 3. So h is concave up at t equals 3. This part in B would be your explanation. Sorry, this part in blue would be your explanation. Anyway, hope this was helpful. There's a lot of I can almost guarantee differential equations will be a free response question. And there's a lot of different types of questions that they will ask involving differential equations. So hopefully these will help you guys tackle a couple of the different applications. Have a great day.